Welcome to this short recorded video where we will go over the instructions for the homework assignment notebook associated with Module 4. Before you begin, you should make sure to import NumPy as NP, the PyPlot module of Matplotlib as PLT, mount your Google Drive, and set your module paths to wherever you've had the MyFunction classes and differences modules previously stored on your Google Drive from the previous files, notebooks that we've worked on in this course. So this first path that I have is for the external activities notebooks associated with Module 4, and that's where the MyFunction classes .py file is stored on my Google Drive. And then in the third module in the lectures notebook is where I have the differences module stored. So wherever you have your files stored is fine if you're not following the way I'm doing it in these notebooks. You just have to make sure that you change these paths to whatever the paths are in terms of the folders containing these files. And maybe you have both of these files in the same folder, in which case you'd only need one path variable there. So after you've done that, I have some information here that you can read through. I talk about how root problems naturally arise in the optimization of smooth phenomenon. All that I really mean here is that smooth phenomenon is describing some sort of functional response that is differentiable. And we've seen previously that where derivatives are equal to 0 are places where functions generally take maxima and minima values. So if you can find the roots of a derivative, then you're finding the locations where you should be able to optimize the original function, or at least they're the candidates for the optimization of that function. So there's some motivating examples that I have here as well. And again, you can read through all of this. And one of the main points though that I want to make here is you don't really need to know how to compute derivatives. Again, we will just use the differences.py module in order to estimate derivatives. And then we're going to try to find the roots of those estimated derivatives. That's all we're doing. So as far as this first problem goes, it's to minimize your cost in order to maximize your profits. So there's a narrative here that I'll read parts of, and an important note to make is that all the code in this problem is done for you. You are prompted to provide some code comments, some doc tests, and interpretations in markdown cells throughout. So that's what you need to do for this first problem. So as far as the narrative goes, it's kind of a joke here. It's just you've discovered that you are the world's best pasta sauce maker. Congratulations. You should profit on this discovery. People love your sauce so much that they want to buy it a liter at a time. A liter is 1,000 cubic centimeters. That's a lot of sauce. You can almost taste those profits, can't you? There's only one problem. You need to find liter-sized glass containers for your sauce. You talk with your co-packer and they cannot find a distributor of glass containers that makes the quality and quantity of liter-sized containers that you need. But your co-packer has a suggestion. We can design and make our own containers. What a great idea. Your objective is very simple then. You want to design a liter-sized glass container that minimizes the cost of production and thus maximizes your profits. However, there are some constraints. This is a glass container. It cannot have edges or corners. So the shape requirement is that it's a right circular cylinder. So if you don't know what that is, I've provided a link here so you can see a picture. It's a right circular cylinder. It's like a typical can shape or jar shape that you typically see at the grocery store. So we will ignore the slight curvature that you almost always see near the bottom and top of the container for simplicity. We'll assume that it has a solid glass bottom, otherwise the sauce will not stay in the container if it's just like effectively a cylinder with no top or bottom, and an open top because the sauce needs to get poured into the container during production before a lid is screwed on to secure the contents. So effectively, if you think of your cylinder, the sides are made out of glass, the bottom is made out of the glass, and the top is open because you're going to screw on a lid to the top. So if you go through all of that and you say, okay, using some geometry, what are the things that you find out is that the surface area of the container you specify with a base radius of r for the circular base and a height h for the height of the cylinder. The surface area of that is given by pi r squared, because that's the area of the base, plus 2 pi r h, 2 times pi times r times h. And that's the surface area of the cylinder part without the bottom. You're adding the bottom surface area here. So the volume of a right circular cylinder is simply given by pi times r squared times h. So what you know is the volume needs to be 1,000, but you want to minimize the surface area because the surface area is describing the amount of material, the amount of glass you're going to need in order to build this. So you want to minimize surface area, which is pi r squared plus 2 pi r h, subject to the constraint that pi r squared h has to be 1,000 so that you can put 1,000 cubic centimeters, a liter of sauce in this container. So if you use that constraint and solve for h, you see that h is equal to 1,000 divided by pi r squared. And if you simply substitute that back into the surface area equation, you see that the surface area, written only as a function of the radius, is given by pi r squared plus 2,000 divided by r. The only obvious constraint that you have now is that your radius of your circular base has to be positive, right? Otherwise, there is no cylinder. So r has to be something that's greater than 0. So all the positive r values are fair game. But what should you choose? That's the question. You need to optimize. So what we want to do is minimize s. So we want to try to take a derivative of this function as a function of r, the derivative of s as a function of r, try to find where that's equal to 0, and see what that means in terms of what the best surface area should be. Once we have that r value, we can solve for h because we have that relationship 1,000 divided by pi r squared. Now, if we do this to 2 decimal places, because assume that you're using machines to actually construct this, and that they have a tolerance of up to 0.01 centimeters in terms of the accuracy of the containers that they can produce. The value of r that minimizes the surface area to 2 decimal places is 6.83 centimeters. So I've already solved this for you. I'm already telling you what the answer is. What we can do is use what we've learned in the Part A lecture notebook, as well as the previous notebooks, to approximate this answer. So let's go ahead and develop intuition about this problem. But right now, maybe I'll just pause. Maybe you want to just take a second, read through some of the parts of this that I skipped over, and then come back to this video as it continues on to read through the individual instructions for each of the parts of this problem. So for problem 1A, I'm having you develop intuition about this problem. It is always good to build some intuition about a problem, and that's what we're doing here. What you first need to do is add a doc string. A doc string always goes at the top of the function. So add your doc string here, and it needs this 3 tick marks, and then put in the comments about the doc string. What should you put in? A description of what the function is, a description of the inputs, and a description of the output. What is it doing? That's the contents there as a doc string. Also add a doc test, and then add comments to the function. You might also want to check that your doc test passes. I'm going to know if it does by doing a calculation, so you should show that it passes as well. And then add comments. Add comments to these various lines of code to show what they're doing, to explain what this function is. There's only really 3 lines of code here, so you should be able to comment them all. Make sure, again, I said this to demonstrate that your doc test passes. If you have a doc test but you don't show it passes, you will get no credit for that part. So I'm defining the surface area. And I'm basically making it so that r could be given as an array. And so if any of the values of the array happen to be less than or equal to 0, I'm raising a value error because the circular base requires r to be greater than 0. And you can try to call this function. Here's a good thing to do. Run this code cell. And then if you call this, so I'll just put a code cell here, surf area, and let's say I put -1, a value error is raised and it prints the error message that I have here. So something to just test. It's a fail safe to make sure that no r value is given, and the fact that I'm coding this so that r could be an array. That's why I need to use the np.any function there. So that's kind of a new thing that you might not have seen yet. The surface area function is then coded. I take the pi value, that is the numpy constant, np.pi, I multiply it to r, that is squared, and I add to it 2,000 divided by r. That's just what this formula was right over here. That one right there. So that's all I'm doing in that function. And then I want you to add, and I just want you to comment it. Again, add the doc string, add the doc test, and demonstrate that your doc test passes. So I'll just go ahead and put here and just, show your doc test passes here. I'm just going to do that. And so you should import doc test. You should review how to do that. Again, you might have to go review an older notebook to see how to do that. Then I want you to add code comments to all of the code cells below to explain what is going on, and use markdown cells to contextualize results, explain, interpret the results. So here I'm producing an array of r values, I'm creating a plot, and I'm describing its size. I have a title, a y, and an x label, and now I'm plotting the r values from 1 onwards and the surface area evaluated at those R values. Why am I using 1 there? There's a 0 here, and there could be an issue if I did that. So that should be able to answer your question in terms of also some information that a code comment kind of needs to have on line 4. Now, if you run that, you see here is a graph of the surface area, and you can see that it's minimized right around where 6.83 is. Of course, how did I figure that out? Well, on the same plot, if I plot that function, but then I create the twin axes, so it shares the x-axis, but it has a separate y-axis, and on that y-axis, from my differences module imported as diff, I am using the center difference approximation, and I am computing the approximate derivative of the surface area, and I'm plotting that. All right, and again, add code comments to this code cell. If I run this, one of the things you see, and it's of course also demonstrated right here, is I'm putting a vertical line where 6.83 is. And if you notice where that 6.83 is, that's right about where that red curve passes through this horizontal line, which is associated with the y value on the y-axis of 0. So that's right around where the derivative is equal to 0. There's only the one spot. The derivative goes from negative to positive, which meant the function was decreasing, and then increasing, which means that's where a minimum occurred. That's what's also called the first derivative test. So I'm just using the information that the derivative gave me, along with its root and its sign on either side of the root, to determine is that a maximum or a minimum. So your interpretation of what is shown in the plot goes here, and I've kind of already given a hint on that in terms of what I've said. So you might just want to pause the video, try to do 1A right now. For problem 1B, I show you how to approximate the optimal radius through brute force, right? How do I actually try to estimate where the root of the derivative is? So since r is greater than 0, we may just be tempted to search for an optimal r in the interval, let's say 0 to 40. You know it's got to be greater than 0, but maybe you go like, yeah, I've never seen a jar that has more than 40 centimeters in radius, which would be 80 centimeters in diameter. And of course, if you do a conversion inches, you'd be like, that's a pretty big jar. So that seems unlikely. So you kind of just pick some bounds and you say, all right, I know that r equals 0 is meaningless, which is why we want to consider r values in the half open interval. And you want to see how we avoid that again below. That's where we have this one grid, basically that one slicing here, starting at 1, which is really the second input, the second component of that r. So I'm picking 100 points in which to search for r initially. So I'm going to do this in brute force fashion. I'm just going to create a linspace array of r values that are equally spaced between 0 and 40, but I want to ignore the first one because it's 0. Again, you need to add code comments to each of the code cells below and interpret the results in the markdown cell. If you're listening to what I'm saying, I'm kind of telling you the very important details that you should be writing. So when I have 100 points, and then I just say, well, like, okay, create the surface values associated with those r points. In fact, I'm using 99 of them because I'm throwing away 1. And then I use the argmin function of NumPy. So this is giving me the index for which to search. And you might ask, like, why am I adding 1 to the index of search? And it's because of this offset of 1. Again, details you should add in your code comments. And if I look at that, I go, oh, 6.87. I thought Troy said 6.83. Well, I only used 100, really 99 points in that search there. What happens if I use 1,000 points in my search? So I'm going to solve for the surface area. I'm going to compute the surface area for 999 points. And then when I do the same thing where I find the index of the argument where this is minimized, and then I say, what is the associated r value for that same index? And again, because of the offset of 1, I have to add 1 to it. And I'm just rounding it again to 2 decimal places because I'm assuming that the machines can only machine the radius to a tolerance of 0.01 centimeters. You see it's 6.85, and you go, well, Troy again said 6.83. Here's a super refined search. Do 10,000, meaning 999 points, again, because I'm avoiding 0. Compute the surface area. And now let's look at that output, and you go, 6.83. Finally, we only had to solve for the surface area 9,999 times in order to get 6.83, which is an answer kind of already know has to be the case. Now, your interpretations of the above code and results go here. If you were just listening to me talk, you should know basically how to interpret what's going on in terms of the spacing of these r values, the quality of the answer. It's based on this refinement of just using more and more r points that are kind of spaced closer and closer together in order for me to estimate this. So just take a second. You might want to pause this video, and answer. And remember, code comments and interpretations of the code and the results go here. We now attempt a more elegant solution than the brute force approach that we just saw above. So the brute force approach is certainly not elegant, but it does get the job done. The question is, can it always get the job done? Well, what if the function s was really expensive to evaluate? The one we're looking at is not, right? This Python code executes very quickly because it's a very simple arithmetic operation to compute the surface area of a right circular cylinder with a closed bottom. It just doesn't take a lot of time. There are many functions in practice, though, that are very expensive to compute in terms of the amount of time or resources required to evaluate them. For example, in reservoir engineering, which is a field where I've been asked to review many articles for in different journals, simulating the optimal net present value, NPV, of a new project is critical in management decisions about whether a project is worth pursuing or not. This is something I've had to learn about as a reviewer for different journals. But simulations of subsurface flow often involve complex partial differential equations discretized over large physical domains that may require a supercomputer to solve. Subsequently, it may not be feasible to compute more than a few simulations, like 20, 30, 40. The idea that you compute it 10,000 times is just a lot of times unreasonable. Like, it's just not possible. You don't have the time or the resources to do that. So the brute force option, while it could work always in theory, because you're just I'm just going to keep evaluating the function at all the inputs I possibly can, and then just find which one minimized it. But that might require so many solves that it's just impractical to do in many settings. So what we do is we say, well, imagine that we implement a version of the algorithm for the bisection method that we saw in the Part A lecture notebook to approximate the R that makes the center difference approximation of the derivative equal to 0. So we're going to use h equals 0.001 when calling this finite difference function. We're going to use an interval of 1 to 40, and because it just, less than 1 is even kind of silly. So we think it should be between 1 and 40, and a tolerance for the interval length of 0.005. Again, that will ensure the estimated optimal radius is within the achievable 0.01 centimeter tolerance. The version of the bisection algorithm used here also outputs the actual number of iterations used to achieve the desired tolerance. Actually, I am not doing that. I was doing that before, but I am not going to do that now. You can estimate how many times it's done. So what I want you to do is use a markdown cell provided below. That would be this one right here at the bottom that's highlighted, your comments comparisons for problem 1, so you go here. And I want you to comment on the upper bound for the number of times S must be evaluated to achieve the desired tolerance in the algorithm and how this compares to the brute force approach. So you can figure this out. If you look at this 0.005, you just kind of look at, well, here's the interval that starts at length 39. How many times do you have to divide that in half until the interval is less than 0.005? And then if you think about it, every time that we estimate this derivative, every computation, so every time we bisect, we have to evaluate the function 2 times because we're using 2 function evaluations to estimate the derivative. And because it's based on this finite difference scheme. So think about that in terms of how many times that function s has to get evaluated in order to achieve the same tolerance we saw that required 9,999 solves here. It's going to be a lot less is the point. So here what I'm doing is I'm creating this function object from my fancy functions, my function class that I've imported as myFC, and I'm creating my functions enhanced. Notice I'm creating a lambda function as a function of R that is based on this center difference approximation of the surface area, with h being 0.001. A is 1, B is 40 for the interval where I'm approximating where I'm looking for a root. I set n to be 10 here, but you could actually, I'll just leave n to be 10 because you'll see what happens. When n is 10, if you look at the rounding here, if you were to round this would be 6.83. So within 10 intervals, even 10 iterations, it was fine. If you go to 20 and you run this again, you see it's 8.319. Did it stop there? Like, let's see, with, I don't know, yeah, it seems to be that even with 15. So you can play with that n value just to see exactly how many times it takes to achieve the tolerance you want. I think it's just cutting out before it reaches this particular tolerance in some cases. But either way, if you do this rounding, I'll just leave n to be 15 here in the code I give you, but if you're watching this video, just feel free to play around a little bit. you can see exactly what's going on in terms of the final interval that we have here. Look at its length. It's around, I think it's around 0.005 or so. Yeah, I think so. It's close anyways. And that seems to capture a good approximation of the root to two decimal places, 6.83. And so again, just think about how many function evaluations were required to get that compared to what we just did. So I want you to comment on that. That's really what you're asked to do here. So I've done all this code for you, but what I'm trying to get you to see is these algorithms for estimating roots, doing things, they provide elegant ways and cost-efficient ways of getting information that is critically important for optimization. But here we're just doing it in a specific example of this jar. So again, you might want to pause the video and solve this part of the problem. We are now at problem 2. We forgot the lid. How did we forget the lid? So yeah, right, we kind of forgot to account for the cost of the lid in the container. Oops. Suppose that the cost of the materials for making the glass part of the container is given as a thousandth of a cent per square centimeter. And basically, in other words, it cost 1/10 of, or a thousandth of a dollar. I think that's the way I'm doing that here. So it costs 1/10 of 1 penny per square centimeter of glass needed. So if you're buying it in bulk, you can get it pretty cheap. It's 1/10 of 1 penny per square centimeter of glass needed. Suppose the cost of the materials for making an aluminum lid is $0.002. So in other words, it costs 2/10 of 1 penny per square centimeter of aluminum needed. Why? I'm just going off the assumption that metal is a little bit more expensive than glass. I think that's a reasonable assumption. I'm going to assume that it's twice as expensive as glass per square centimeter, and assuming some uniform thickness for each of these. So that means that the total cost in US dollars to produce a single liter container with a lid is actually now given by 0.001 times the surface area. That's what this pi r squared plus 2,000 divided by r is. That's the surface area. And then 0.002 times pi r squared. Pi r squared is the surface area of the lid. So this is a good function to actually describe the actual cost. So before, if we were just thinking of the jar being open and we didn't have a lid, the surface area is directly proportional to the cost. So minimizing the surface area minimizes the cost. But we actually need to minimize the surface area, but we don't want the jar to be maybe really wide, because then the cost of the lid might start to overrun it, because the cost of the lid is twice as much per amount of surface area as the rest of the jar. So there's some balancing act going on here. So this cost is produced in the function total cost below. So right here, I want you to again add comments to this, a docstring and a doctest. And of course, make sure your doctest passes. All right. So what I want you to do is look at this total cost function. In here, it's the same thing. I need my radius to be positive. I'm computing the cost of glass. Notice I'm just computing 0.001 times the surface area of R. And then I'm taking the cost of the lid, which is just 0.002 times the pi r squared. But I'm using that pi library constant from NumPy. And then I'm just adding those two things together and returning it. That's what I return out of there. So add your docstring right here at line 3. That's where it goes. Again, you have to have those 3 tick marks. Add your docstring, describe the inputs, describe the purpose of this function, and of course what it's returning. Those are the proper things to include in a docstring. Add comments to every line of code. Okay, there's basically 5 lines of code, because the return is a little bit less trivial than what we've seen before. And then of course have your doc test and make sure your doc test passes. But what I'm really asking you to do is redo the problem 1, parts A through C. So the way you do that is just redo this analysis, but it is a lot of copy and paste. You can basically just copy and paste all the code you saw above, and everywhere you saw surf area, just replace with total cost. But then when you're looking at something like, let's say, DSDR, like, let's see here where I did this, like DSDR, obviously that should maybe be DCDR, because the capital C is the cost instead of S. But otherwise, it's just take all these code cells that you've seen here in 1A, from 1A on down to here, to like all these code cells, just copy and paste them in here. You're gonna have to create a lot more code cells, or if you copy them and you paste below, it will just automatically add them. And I want you to just put them all in there and redo the analysis. So everything I was asking you to do above, do it here, and you might need to make sure to change your code comments so that they're referring to the total cost instead of the surface area. In the end, what I want you to do is I want you to compare the optimal dimensions. So you've been computing R, compute H for both of these, and so this is problem 2 actually, so I'm going to just change that right there where I said for this and problem 2. So yeah, for this and problem 1 is what I really meant. So all right, there we go. So I want you to compare these optimal dimensions. What are you going to get? What do you get from for the R and the H values for problem 1 versus problem 2? And then I want you to look at what the typical things are for a jar, the typical dimensions. And if you do a quick online search, I did, a typical 24-ounce pasta jar, which is equivalent to about 7/10 of a liter, so 700 cubic centimeters. So you're making a bigger jar here. That has a height of about 6.61 inches with a base diameter of 3.37 inches. And a diameter is just 2 times the radius. Now, all that matters is basically the ratio. Inches to the diameter or to the radius. Like you could take this and divide the diameter by 2, you'd get the radius. And look at the ratio of height to radius. Which of these problems, problem 1 or problem 2, is producing results that look more like a typical pasta jar in terms of the ratio of height to diameter? I want you to comment on that. I mean, spoiler alert, you should find, if you're doing everything right, that it's this one. It's not exact, but it's closer. And what that tells you is the people that are making and selling pasta sauce and pretty much every jar, the typical dimensions of this, they went through a problem like this where they minimize their cost. They're not stupid. They're going, I want to sell the volume I'm selling, but I want to minimize the surface area, because the surface area is what is the total cost, because that describes the cost of the materials I have. If you decide you're going to sell, X amount of a volume of some sort of liquid or solid that you have to package, then the packaging, the surface area of your packaging is going to define what your costs are for the packaging of that. And you want to minimize your cost. If you're running a business, if you have any sense about you want to make a profit. One of the best ways to ensure that you can make a profit is minimize your cost wherever you can. So I want you to look at that, see how this really goes through, and it really drives home the idea of finding roots of derivatives. It's great for optimization. So you might just want to pause, go through problem 2. Again, it's just repeating problem 1, but it's going to force you, just like before in problem 1, I was forcing you to add comments to basically all the lines of code. You're going to go through it again, but making sure you have it with the total cost function. You should know that you should get a height and radius that's a lot closer to what we have now, or to what the optimal one is in practice. It's not going to be exact, but it's going to be closer if you did it right. And then just comment on all this stuff and make sure to just pay attention to what changes in the code. So again, total cost function, you just basically paste all your other code cells below this, and again, make sure your doc test passed.